Video we will talk about the covariance of the multinomial gap. What is a multinomial random variable or a multinomial distribution? So let's say we have an experiment that can result in r possible outcomes, and the possibility of the experiment resulting in any outcome, ith outcome, is pi, and then we perform the experiment independently n times, and then let xi be the number of times outcome I occur. And obviously if uh, there are r outcomes, then I should be from 1 to r, and we have xi 0 to n, because xi is the number of times the outcome I occurs. So the minimum number of time it can occur is 0 out of n experiments, and the maximum number of times it can occur is n out of n experiments. And then probability p of x, the joint probability, or the PMF, probability of x1 is equal to some x1, x2 is equal to some x2, and up to xr is equal to some xr, is the multinomial distribution, and the PMF is given by this expression here. Okay, and then due to the definition of probability, obviously if we sum over all the possibilities of x1 to xr, this should sum to 1. Okay, and then we have already proved that the expected value of any xi is n times pi, and the variance is of any xi is given by n times pi times 1 minus pi. Note that this is the same as the binomial distribution. Why? Because the binomial distribution is just a special form of multinomial distribution with n is equal to 2. Okay, now we talk about the covariance between xi and xj, and note that the procedure we will follow is very similar to what we did for the variance here. Okay, so let's start here. So what is the definition of covariance? Covariance is given by the expected value of xi times xj minus the multiplication of expected value of xi times expected value of xj. And this we already know that this guy is equal to n times pi, this guy is equal to n times pj. So then we get n squared pi pj here. So let's call it expression A here. Now our target is to calculate this guy. Okay, so for this one, let's start by writing the definition. So we have, and for without loss of generality, we will use I is equal to 1 and j is equal to 2. Okay, so then let's start. So we have E of x1 x2, this is equal to summation x1 x2 x1 x2 p of x1 is equal to x1 comma x2 is equal to x2, and we have xr is equal to xr. Okay, now we can plug in this from here, so then we can say, and then obviously we have x1 plus x2 up to xr, this is equal to n. So then this guy is equal to what? So then what we do is we say the same thing here, but I'm going to skip it just to save some space. We can say x1 x2 n factorial divided by x1 factorial x2 factorial up to xr factorial p1 to the x1 up to pr to the xr. Okay, now this is again the same story here as here. Now this x1 can be simplified with x1 factorial here. This x2 can be simplified with this x2 factorial here. So what I'm going to do is I'm going to do some steps one at a time. Okay, so then I will do this. So I'll say n factorial divided by x1 minus 1 factorial x2 minus 1 factorial and up to xr factorial, and this one I will say p1 x1 minus 1, and I will put one p1 outside, and then I will say p2 x2 minus 1, and then I will put one p2 outside, and then this is just pr to the xr. Now we have to do a change of variables. So the change of variables, we will do x1 prime, this is equal to x1 minus 1, and then x2 prime, this is equal to x2 minus 1. Okay, and then since my summation of x1 plus x2 plus xr is equal to n, so I will say x1 prime plus x2 prime plus this is plus xr, this should be what? N minus 2. Why n minus 2? Because we take away 1 from here, we take away 1 from here, and then therefore we have taken away 2 from the total sum of n. Okay, okay. So now let's continue with the change of variables. Now what do we have? We have p1, p2, and then this one is, now let me write it, x1 prime up to xr, where x1 prime plus x2 prime plus xr, this is equal to what? N minus 2. Okay, so then we will have n factorial, and then this is x1 prime factorial, x2 prime factorial up to xr factorial, and then we can say p1 x1 prime, p2 x2 prime up to pr xr prime. Ah, not prime, pr xr. Okay, so now this n factorial is a problem because this sum is n minus 2 and this is n factorial. Other than that, everything is under control. But if we change this to n minus 2 factorial, we will have this whole sum equal to 1 because of this formula here. If this formula in this formula, if we replace n by n minus 2, we will have n minus 2 here and n minus 2 here. Okay, so this is very easy to do. So we will use n factorial. This is equal to n times n minus 1 times n minus 2 factorial. So what I'm going to do is I'm going to change it to n minus 2 factorial and then put n times n minus 1 here. Okay, so now this guy, this is equal to 1. So my answer is what? My answer is n times n minus 1 times p1 times p2. Okay, so now this is the expected value of x1 x2. So now, but we are interested in what? We are interested in the covariance. So now this guy is what? This guy is n times n minus 1 times p1 p2. Okay, so now, okay, so now covariance of x1 x2, this is equal to what? This is equal to n times n minus 1 times p1 p2 minus this guy, n squared p1 p2, which is equal to negative n p1 p2. So this is my covariance of x1 x2, and needless to say that covariance of xi xj will be equal to negative n pi pj. So in practical, terms, what does it mean? It means that if the number of outcomes of one type of outcome increases, so it tends to decrease the other, some other output. Why? Because the sum of all of them, all the outcomes, should be equal to n. So if we increase one number, we have to decrease some other number to make to keep our sum constant. Okay, so this is the covariance of our multinomial distribution. Okay, so now, so as an example, if we have n is equal to 3 and p1 is equal to 0.2 and p2 is equal to, let's say, 0.4 and p3 is equal to what? Because they should be summed to 1, right? So this should be 0.4 again. If this is the case, then we have covariance matrix. So we can say covariance of x1, x2, x3. This is, so this one, the first one is 3 times 0.2 times 0.8. The second one is negative 3 times. P1 is what? 0.2. P2 is what? 0.4. Third one is what? Negative 3 times. P1 is what? 0.2 and 0.4. Okay. And then this is again, because this is symmetric, so I don't need to do these ones. So this is what? 3 times 0.4 times 0.6, and this is what? Negative 3 times 0.4 times 0.4. Okay, and this is again 3 times 0.4 times 0.6. Okay, and then this is equal to this, and this is equal to this, and this is, because this is a covariance metric, it has to be symmetric. So we only need to calculate the upper triangle or the lower triangle with the diagonal here. So this is the way we calculate the covariance matrix of a multinomial distribution. So as a recap, we calculated the covariance of the two outputs and we came up with this expression. And then once we have this expression, we can form our covariance matrix. And the way we reach this expression is by, again, our the same old good old trick of change of variables in a summation and doing some manipulation using the fact that this sum is equal to 1. So this is it about the covariance of the multinomial distribution. Hope it was easy to understand, and thanks for watching. Hope you liked the video.